Hello! This video, we're going to solve this differential equation. Now, we're really looking for the general solution, y in terms of x. Now, first I would like to note that y equals 0 is a solution. That is, y being identically 0 is a solution. In other words, y equals 0 for all x. Right? And you can check that this is a solution to this differential equation, right? We see that because y equals 0 for all x, ky equals 0 for all x. So yes, the right-hand side is 0 for all x. But also, if we take the derivative of this thing with respect to x, we get dy over dx is 0. So yeah, the left-hand side is also 0 for all x. So yeah, this is a solution to this differential equation. What that means, though, is that every other solution to this differential equation is one where y is not identically 0. So we are going to assume that in this differential equation, y is not identically 0. Now, what it means for y to not be identically 0 means that there are y values where y is not 0. But that doesn't mean that we couldn't have y values that are 0. But it turns out that if y as a function of x satisfies this differential equation, turns out if y is not identically 0, then y can never be 0. And I would like you guys to wrestle with this idea. I'm not going to justify it any further, but the reason why this is important is because it justifies why we're allowed to divide y to the other side. Because y is never 0, we can divide y to the other side of the equation. Okay, and now performing separation of variables, we'll move dx to the other side. And so now we're ready to integrate both sides. Now, as for the left-hand integral, we know that the integral of 1 over y is just natural log of the absolute value of y. And I'll add a constant of integration plus c1. On the right-hand side, the integral of k dx is just kx. And I'll add my constant of integration plus c2. Now notice we can subtract c1 to the other side. Now when we take a constant and subtract it by another constant, we also get a constant. So really, I'm going to rename c2 minus c1 to a new constant, c3. So c3 is just any constant. Okay, so remember, we're trying to get an explicit solution, y in terms of x. So we're solving for y. All right, and to do that, let's start by doing e to the power of both sides. You can see why we did this. The e and the natural log cancel out, so we're left with absolute value of y. And on the right-hand side, we could use our properties of exponents, where we really just have e to the power of kx times e to the power of c3. Now, moving over here, now notice we have e to the power of a constant, but really, e to the power of a constant is also a constant. So I'm going to rename e to the power of c3 to a new constant, c4. And I'll just flip these around so it looks nicer. Really, this is what we have now. But here's the thing. c3 could really just be any real number for our constant. Can c4 be any real number for our constant? Turns out no. c4 must be a positive constant. The reason why is because c4 is equal to e to the power of c3. And when we take any number and do e to the power of it, well, e to the power of anything is always positive. And so that's the reason why c4 must be positive. And turns out, in general, c3 could be any real number. c4 could be any positive real number. But now that we know that, how do we get rid of the absolute value of ours from y? Well, think about what the quantity on the right-hand side means. It really is equal to the absolute value of y, and absolute value means that this quantity is the distance that y is from 0. So, y is either the positive or negative of this quantity. Really, I have two possibilities of what y could be. Y is either plus or minus this. So we're going to consider case 1, where y is the positive of this thing. Now I'm just going to rename c4 to a new constant c. And so really, since c4 is equal to c, and C4 is greater than 0, we have that C must be bigger than 0. So this would be my general solution if I had case 1. Now case 2 is if we instead had the negative of this. Now, similar to what I did in case 1, I'm going to rename negative of C4 to a constant C, just like this, and since C4 is greater than 0, negative C4 is less than 0. So in other words, negative C4 is equal to C, so C is less than 0. And so these two cases covers all possibilities of what y could be as a function of x. And notice in each case, we have the same formula. So really, in general, y is equal to c e to the kx, where c is any constant that is either greater than 0 or less than 0. Now, it's unfortunate because there is no case where c could be equal to 0, because then that would mean we would be able to say y is equal to c e to the kx, where c is any real number. But luckily, we know that this is also a solution to this equation. But saying y is identically 0 is another way of saying y equals c e to the kx, where c equals 0. So really, these are the two solutions where y is not identically 0. This is the solution where y is identically 0. So really, these are all possible solutions to this differential equation. But notice, in general, we can rewrite all three of these as the same thing. So in general, we just have y equals c e to the kx, where c could be either greater than 0, less than 0, or equal to 0, but then that means c could be any constant. And so this completes the derivation for the general solution for y explicitly as a function of x, right? And so yeah, this was a derivation of the general solution to this equation. And so yeah, there was quite a bit of technical detail here as well, which will sometimes happen. But yeah, this is pretty much how you could work through deriving the solution to this. So yeah, that's pretty much it for this video.